Hi everyone. Thanks for coming. So Niayesh Afshordi is here today. He's visiting from PI in Waterloo. Niayesh is an expert in theoretical astrophysics and cosmology and particle physics. And today he'll be talking to us about cosmic nanostructure.
Thank you very much, Phil, for the introduction, and thank you for the invitation. Thanks everybody for coming. It's always fun to be back here. So it was a challenge. So I'm going to tell you about cosmic nanostructure, which are basically a couple of papers that are coming out this. So one is already on the archive, but it's going to be updated with much better figures this evening. And then there's another one that's coming out for the first time this evening. But it's always challenging. It was very challenging to decide what to talk about. Here's what I'm not going to talk about, just in case you were trying to figure out what I was going to talk about. So there are all these things that I've worked on over the last couple of years, but I'm not going to talk about them. Quantum black holes and gravitational wave echoes, cosmological non-constant problem, modified gravity, dark energy, Big Bang, quantum gravity, dynamical friction, the cosmic neutrinos, holographic cosmology, cosmic zero modes, accretion disk. I'm not going to talk about any of them, but if any of them catches your eye, I'll be happy to discuss them with you later. I'm going to talk about bland, boring astrophysics, since this is Canadian Institute for Theoretical Astrophysics. So there wouldn't be anything speculative in what you're going to hear, unlike all these other topics. Almost. So what are the cosmic structures that we're familiar with? This is figured due to your own Rene logic. Is Rene here? I don't know. I guess not. It's traveling, yes. So this is a very nice picture which shows, it's a little bit dated, but it shows structures on various scales. This is in mass, but you could also show distance. These are the biggest scales that we observe in cosmos. These are the smallest scales that we observe, ranging from cosmic microwave background down to Lyman alpha Firax and everything in between, various types of structure. And these are scales that we understand relatively well. There are, of course, theoretical uncertainties, but we have a good observational handle on what's going on. However, if you want to go to much smaller scales or much larger scales, there is really very little observational handle on what's going on, at least cosmologically speaking. And so there is basically lots of uncertainty. So the first time I gave this talk, it was on the International Day of first International Day of Dark Matter, which happens to be the Halloween, the last Halloween. So that's why I have the ghosts here. But that's basically we don't really know what's going on. And the goal of this talk is basically to discuss how we can put more observational light, basically, objectively on what's going on down here when it comes to cosmic structure. So there have been a lot of discussion about dark matter on small scales. There have been lots of hot topics that have captured headlines, from missing satellite problem to angular momentum problem, cosp core problem, too big to fail problem. And if you've come to these seminars in the past 20 years, you've heard probably these mentioned many, many times. It has to do with the fact that dark matter on the small scales is predicted to have many structures, and these structures have substructures, and substructures have substructures, and this goes on for many, many decades. However, if you compare the properties of these structures with properties of observed satellites or other observations of dark matter on a small scale, so this is just one example. I don't want to get into the details. This is the too big to fail problem. Seems to be some discrepancy between predictions and observations.
Just one question. So are you saying that these are still problems?
So here is a sense. So these are the solutions. There could be gastrophysics that could solve these problems. There is dark matter physics. So these are
But I thought there was like Carl Schrank would say that conventional physics would solve.
Okay, so that would be gastrophysics, right? Which is, I think, the term invented by Dick Bond, I believe. So if you're an astrophysicist, the thing astrophysicists can solve all this. If you're a simulator, if you're a particle physicist, you have your favorite model of dark matter, and there are hundreds and thousands of papers. Well, not hundreds of thousands, hundreds of papers, I should say, proposing various dark particle physics solutions. And if you're a fan of modified gravity, which is less popular, but nevertheless you think that these actually point to modification of gravity. Now, my point of view on all this is that if you torture the data long enough, it will confess to anything. And that's true for both observational data and simulated data. So of course, sure enough, this came out last week, for example, or 2 weeks ago, says that and these are from the same people who proposed the Toobigtofail problem, that they did simulation with super duper feedback, and then this is feedback in realistic environments, and they claim that they solve Toobigtofail and missing satellite problem. So the lesson is that real data is complicated, especially if it involves baryons, and essentially it's very easy to come up with problems, and it's very easy to solve them. So basically, depending on your point, if you're in the mood to invent new problems to solve them. But basically, it seems that same people could invent problems and then solve them. So the other part of this problem, which is closer to observations and is more immediately testable, because of course, I mean, feedback and a star formation is a complicated multi-scale problem. So it's easy to imagine that, OK, so it's very hard to understand. It's like weather. So if maybe I mean, you won't really know easily that there is a problem. But the other side of this is, I mean, places where you actually can see this happening, where you actually see stars forming and things cooling. And the most prominent place of those is where we face the so-called cooling problem. So the classical cooling problem is basically the fact that if you look at clusters of galaxies, you see this hot gas, which basically makes up most of the matter, most of the ordinary matter in them. But the cooling time for this hot gas becomes shorter and shorter if you go closer and closer to the centers of these clusters. And you see that this is the Hubble time, and the cooling time gets shorter and shorter as you go smaller. So these things cool much, much faster than the Hubble time allows. So the real question is, why is there anything left there? Because these things should be cooling basically incredibly fast, and it would be very hard to keep them there. The obvious answer is you need some heating to keep these there. But nevertheless, it should be a very fine-tuned situation because, I mean, the cooling happens very, very rapidly and across many, many temperatures and everywhere. And to keep the hot gas there, you have to basically compensate that everywhere across the ranges of temperatures, basically in the space, time, and temperature. And I mean, there are solutions to do that. The most obvious one is AGN jets, shocks or sound waves, turbulence, turbulent heating, supernovae feedback, conduction in plasmas at these high temperatures could be important. And it's probably most likely a combination of these that could solve this problem. But it just says that even on these scales where we can almost see things, resolve things with our telescopes, I mean, you have a very complicated situation. And so far, there isn't really a simple picture or theoretical or observational exactly about what's exactly going on down here. Yes?
AGN jets, I can imagine, will cool and maybe heat as well. So which would it be?
Well, I mean, if this is to solve the problem, it must be heating. Yeah.
I see it on this drawing. It's not obvious.
No, it's not. But I mean, of course, if it doesn't, then it's not a solution. So these are all, I guess, proposals. So now there is observational evidence for this in the sense that there are these cavities that people see in X-ray data. And these cavities seem to be, well, at least some of them are around the lobes of AGN jets. And if you kind of compute the energy in the cavities, they're comparable to the energy that you need to, so basically the pressure work in the cavities is comparable to the energy you need to offset this cooling. So there is observational evidence for this, but exactly whether it does the job and all the scales that you need is not clear. But I mean, if you talk to people who come to seminars, this is supposed to be the leading, or some combination of these. But AGN jets in particular would be the source of this, but then it won't be dissipated by turbulence or sound waves. Good, but that's a good point. I mean, as I said, this is really an open question. So there is another side of this cooling flow problem, And that you could see it by looking at the spectrum of cluster cores. So if you have a steady state cooling, now what happens is what I showed you the time scale for cooling. So even if you imagine you have episodic heating scenarios, like every now and then your AGN goes boom, in the meantime, in between those episodes, there would be basically cooling at a lower temperatures. You would have faster and faster cooling, because cooling time basically goes down with temperature. And you could actually, there's a simple model based on so-called isobaric cooling flow, which is based on a steady state and a standard cooling, that tells you how much luminosity you get at different temperatures. And you could basically plug this into some spectral model for Bremner-Strahlung emission, or free bound, and basically plasma emission. And you can predict what is the spectrum of an X-ray gas that, and this is an X-ray spectrum. A spectrum of X-ray gas that emits X-rays within this isobaric cooling flow. If you go out and look, and you see there are all these big lines, metal lines, and the reason you see the lines is that as you go to lower and lower temperatures, you find more bound transitions, because the atoms are not completely ionized. And these are basically atomic lines of these highly ionized ions. If you go and look at an actual spectrum, and this is, of course, this is old, but nevertheless, the situation hasn't changed, you see that, I mean, this is data, and you don't see really evidence for any of these lines. And if you actually want to fit the data, you have to cut off all the temperatures below something, like in this case, it's 2.7 keV. Then you could actually get a good fit with this, for this data. This is the core of a particular, or the inner region of a particular cluster, able to 1835. So a cooling flow, even though it's a physical model, and you think it's on a small temperature, it should be a good model, because cooling happens very, very fast on a small scale. So everything should be in a steady state cooling. It gives the wrong prediction for the spectrum. So in practice, what X-ray observers do, they, instead of this, use a single temperature, multi-temperature model to fit the spectra. But it's not a physical model, because if you're cooling very, very fast, obviously you cannot sit at a single temperature. So, so the situation is not very satisfactory here.
So what fraction is this of the black body? If you had black body emission instead, so what fraction of the luminosity?
This is all black body, but sorry, this is not black. None of this is black body. This is all the optically thin. Yeah.
What fraction of black body? Suppose you had black body emission instead. So what would be the ratio between what you get in the black body emission at the same time?
I don't know the answer, but I mean, these are all optically thin environments. So black body is never a good approximation for this, if that's what you mean by black body, right? So these are all optically thin. So basically, your calculation, you have free bound and bound emissions from a plasma, right? So here's the problem. You still have, this is a similar problem. It's a missing cold gas, but it's a different manifestation of it, is that if you try to fit the spectrum on a small scale, small temperatures, where you expect basically everything to cool, you don't see anything crazy. And the idea is that there must be a solution to this, but exactly the form of the solution is still very controversial and is also somewhat complex. So there is this idea about an onset of thermal instability that is somewhere in the cluster. So this is what you're plotting here. This is from a paper of my colleague, Brian McNamara. This is the cooling time in the centers of cluster, the minimal cooling time, or here the minimum of cooling to free fall time. And here is the amount of molecular gas that's seen in ALMA. And so there are two interesting things here. That is that one is that there is a value, seemed to be a universal value of cooling time around the gigayear, below which you see a lot of cold gas, molecular gas, and above which you don't see anything. And in this ratio, there is a narrow range between 10 and 25, where all the cold gas seems to be sitting there. Above it, there is no cold gas, and below that, basically, there is no region. You cannot, I guess, have anything. And the significance of this number is that this is a range that's predicted, at least this lower limit is predicted to have thermal instabilities. But there is controversy in the literature about whether thermal instability is what's responsible for production of this lower limit, or production of this cold gas to begin with, because I mean, you have cold gas above this limit, but thermal instability is predicted to be here. And there is this debate, which is, I cannot really follow it very well. It's a technical debate between precipitation versus uplift, whether you actually make cold gas from basically cooling hot gas at these large radii, or maybe you have these bubbles that drag along the cold gas from the cores of clusters or from the galaxies in the middle up. But basically, the gist of it is that there's controversy about how you make this cold gas and how much cold gas there is. So
what exactly is the thermal instability? Is it just that the layers, you compress layers, you get very thin layers?
So the thermal instability is, so basically you have cooling and heating, right, going on.
Oh, so this
Yeah.
is
Right.
Okay, so
Yeah.
in this case, couldn't you get regions that are obviously thick?
No, you can never be, I mean, these are very low density environments. You can never get them. I mean, if you get, yeah, by that time you have very cold, you have this molecular gas there. So by that time, yeah, but I think that's when everything is said and done, right? So you have very cold nuggets where they become opticalistic, the molecular clouds presumably. But that's what you're seeing, right? Most of the gas is not in this cold phase. And the real controversy is that how you get this cold gas there, and how is it basically in this narrow range, and why this narrow range to begin with. Yeah. So now with that introduction, so there's basically the thing to keep in mind is that there is all this uncertainty about what's going on the small scales. And so theoretical status of subkiloparsec structure is just very confused. So it would be good to get direct observational handle on them rather than these various theoretical controversies, because it's very hard to make progress in theory in general without observations. So with that introduction, here's what I'm going to talk about. I'm going to talk about two types of nanostructures. There's one in baryons that forms in cooling flows. And the reason I call this nanostructure is I wanted to have one title for the whole talk. But I don't really have a good justification to call it nanostructure. It's just cold gas forming cold stuff. In principle, you make a small molecular clouds out of this and form stars eventually. Then I'm going to talk about dark matter nanostructure. And these are things that are predicted to be in dark matter because cold dark matter is a scale-free model. And these are supposed to be there from the beginning because cold dark matter is cold. And I'm going to talk about how the prediction for this and then observation of that. Actually, for both of these, baryonic and dark matter nanostructure, I'm going to first give you the theory of them, or a revision of the theory for them. And then I'm going to talk about the new observational probe of that. So let's start from the simplest thing. So this is what I mentioned, the isobaric cooling flow. This is literally what it is. The idea is that you have a cooling time that I showed you the expression. It depends on the temperature. Actually, let me go back to this. This is the expression. Sorry, I went too fast. For the cooling. So cooling time is basically the thermal energy density divided by the cooling rate, which goes as this density of electrons times density of hydrogen times what's known as the cooling function. So this is the cooling time, and this is what gets very short as you go to the centers of clusters. And at low temperatures, generally low temperatures, high density, this gets very short. So the isobaric that I mentioned refers to as the assumption that at low, when things happen fast, then you assume it happens at constant pressure. So you assume NKT is constant. So the isobaric cooling is basically saying that the cooling time, or the d log at constant temperature, sorry, at constant pressure, d log T, this is temperature, by d time, goes as -1/T cooling. So that's basically the definition of the cooling time at constant pressure. So if you assume things are in a steady state, you could just take this and invert it and say that the probability of finding a gas particle at temperature log T is, or a gas mass, parcel of gas mass. The temperature log T is proportional to T cooling. That means that the faster the T cooling, so you have this gas that's cooling down, and the shorter cooling time, the faster it cools, so the less likely you are to find gas at that temperature. And basically, the statement is that the conservation of mass tells you this times this should be a constant, right? So that's, and from this, if you know how much gas at any temperature you have, you can plug it into your what is it, Rybickian-Lightman, which is your, I guess, radiative transfer, radiative processes textbook, and that gives you a spectrum, right? So what we did was just do a very simple modification to account for heating. And this is the work with a student who just finished Sharif University in Tehran, and an astronomer in Tehran. So this is Muhammad Julid Haqiqi and Habib Khosrow Shahi. And basically, it's just the obvious thing. If you think there is cooling and there is heating, you need to have both cooling and heating. Right? So the rate of cooling would be basically the same thing you had before, but you have to add your heating here. And of course, if you go through the same logic, then the probability of finding a gas at some temperature would go as 1 over this, which is T cooling, what you had before, divided by this thing, which is 1 minus T cooling over T heating. And you notice at some point this actually goes to 0, so you have to regularize it. But it turns out, since it actually diverges only logarithmically, it doesn't matter very much how you regularize it. But basically, this is a prediction if you have cooling and heating happening at the same time. And it's a very obvious and a straightforward extension of a standard cooling flow. So we call this C plus H, or cooling plus heating flows. So the real question, though, now is what do you assume for heating? And this is where the crux of the argument is. So the idea is that you have this very dynamical, turbulent environment. There is AGN jets, and there are bubbles. There are galaxies going around. There could be conduction. There are all sorts of crazy things happening in the inner regions of galaxy clusters. If you assume you have a turbulence, which is basically if you have things that steering the medium, you expect to have turbulence. In equipartition, which is a simple assumption whenever you're dealing with a turbulent medium in a steady state, and the reason it's a steady state is that everything is happening rapidly compared to the Hubble time, is that the velocity, the turbulent velocity, is of order the Alpha velocity. Alpha velocity is magnetic field squared divided by density, roughly. And is of order alpha, which is some dimensionless number less than 1 times speed of sound squared. And this alpha is known as Shakuros and Niayesh viscosity parameter in the context of accretion disks, and is something of order of 1% or a few percent, depending on the context that you're looking at. Now, if you want to know the heating time, which is the number I wanted to plug in, then I have to basically calculate how long it takes to heat up, given this turbulent medium. And the key thing to keep in mind is that there's a time scale of turbulent dissipation, which is time it takes basically for some eddy to basically become, to divide up in 2 eddies. And that goes as basically R over V. Right? So it's the time scale of a turbulence. So the idea is that if you have a turbulent or Kolmogorov cascade, then you dissipate energy, your kinetic energy is rho V squared. You dissipate it over a time of R over V. So rho V squared over R over V. This would be the rate of dissipating energy. And this is the total energy density that you have. So the heating rate would be the energy density divided by the rate of dissipating energy in turbulence. And if you just plug in the numbers, so R is some size scale. And V goes as alpha times the speed of sound squared, or V squared is alpha times C squared. If you plug in, then you get a number which goes as R over CS, which is sound crossing time, divided by alpha to the power of 3/2. So this is the heating time scale. And this is the key assumption here, because now we know how heating time depends on radius and temperature, because CS is the speed of sound. That depends on temperature. Right? Speed of sound goes as the square root of temperature divided by some mass scale.
Something I don't understand. The Kolmogorov turbulence is dissipating energy just at the very lowest scale.
That's right.
But the lowest scale depends on the viscosity.
That's right.
So this would be, so both R and alpha are dependent.
Right. No. So the Kolmogorov turbulence, you have the long time scale of the eddies, and then as things dissipate, you basically have your eddies that break up and then break up and break up, and then if you become very small, then they dissipate. But
That's the heating. Heating comes just from the the smallest scales.
That's right, yes.
So it means R and alpha are dependent.
Right, so this alpha is not the molecular viscosity, this is the turbulent viscosity, right? So this goes as, depends on magnetic field, basically, in the system.
So how is R defined?
R is some length scale.
Should determined by?
Well, I mean, for our case, this would be the size of the region in the cluster that we're looking at.
But you don't dissipate energy in that scale, in that large scale.
Right.
These are much smaller scales.
Well, sure, but then things become faster and faster as you go to a smaller scale. So the longest time scale.
In turbulence, you don't. You just move the energy from large scale to lower scale, from lower scale to lower scale.
Yeah.
Dissipation only happens.
That's right, right. But the time scale is the longest time scale that it takes. So it basically you.
It's the same scale for all.
Okay.
For all decades.
Well, the cascade rate is the same on all decades. Okay, so I see what you're saying. So it could be a logarithmic correction here. But if you say it's the same, then you have to add the number of decades that you have, but that would be a logarithmic correction. So if it's the same for all decades, then you say how many decades you have, and then you have to multiply. And that's fair enough. So it could be a log. That's why I said this is of order that. Fair enough. Okay. Good. Other questions? Yes?
I thought in Colorado, alpha would be a function of scale as well.
Well, so this is not, this is the alpha on the largest scale, on the steering scale, right?
Which you don't know entirely.
But that's right. So that's what we want to measure, right? So, right. So, but as I said, so as things get smaller, then I mean you're right. So it could be if it's the same time scale, then it could be a logarithmic, or if things could get faster. In either of those cases, there would be either basically this is the right order of magnitude, or there might be a logarithmic correction to it. Okay, good. So that's the prediction. So we have a prediction for heating rate. We know how it depends on temperature and radius. So temperature would be this would be a square root of temperature is the speed of sound. And then we know we have to plug it in this formula, and it's a simple modification of the original isobaric cooling. So let's compare this with observation. It turns out this simple model, which doesn't really have any more parameters than the standard models, or even fewer if you want, works well. So this is an emission measure, which is some measure of how much extras you get from different temperatures. This is the standard cooling flow model. And the orange line is what you get in this C plus H, or the cooling plus heating.
What are the units of the horizon?
This is arbitrary, this is temperatures keV. This is arbitrary units, yeah. So the idea is you're comparing this. And this is the model that doesn't fit any data, right? This is because, as I told you, the cooling flow model doesn't work. This is what you get. You get this spike, and you can guess why you get this spike. Where you get a spike is where cooling and heating exactly balance each other. At a smaller temperatures, cooling wins. So here, this is basically looks like the same as this. They are parallel to each other because probability or emission measure is proportional to the cooling time. But then at this spike, you get basically a lot of gas sitting down up here. And then if you go to higher temperature, is where heating means. And here, you're just heating up the gas rather than cooling down the gas. And in principle, down up here, you could produce cosmic rays through Fermi acceleration and things of that sort if you go very far up. But it's not clear that the steady-state model is a very good model if you go very far up here. So it turns out this model, it fits the data basically for most of the annulists that annuli in Chandra data. So that we look at 5 clusters. This model gives you a satisfactory fit in the sense that reduced chi-square is consistent with what you expect from data. It works much better than the cooling flow because that doesn't fit anything, as I showed you. And even if you compare it with the isothermal model, this is the plot of basically delta chi-squared. So this model has the same number of parameters as the isothermal model. Isothermal model has just a single temperature. Here you have a single parameter, which is alpha, I gave you. And nevertheless, basically on average, this model does better. If you add up everything, the delta chi-square is 7, which means that this model is preferred to an isothermal model at, say, 2.6 sigma. Of course, isothermal model is not a physical model anyway, so it's not terribly surprising to do better than that. But the point is that this is now a physical model because it gives you a full distribution of temperatures, but it also gives you how much cooling you get and how much heating you get. And it also gives you alpha, right, which is something nobody would have thought about measuring that in, at least as far as I know, nobody has thought about measuring that in clusters.
If you go back to figure 2, so you have figure 2.
This one.
And so the green green line is the left curve, and the left curve is the second bin.
No, these are, you don't compare these with each other. Right? So, okay, I mean, if you want to compare it, okay, so this is A2029, which is 7th annular spin. I mean, so, sorry, this 7th is not the 7th point here. So it's, we're not showing all the points here. We're showing all the points that actually give you satisfactory fit. Yeah.
Because it says 7, and it looks to me like number 2. The number 2 is minus 6.
Right. So I was saying, and we don't show all the annuli here. Right. So these are all the ones that can be fit by either of these models. There are some that.
Well, I'm just looking at the left-hand side. They say it's the same object with the
Yes.
right-hand side.
2029, 2029.
Better, meaning delta is going to be negative somewhere.
Yeah.
So
Yes.
it seems to me you're looking at about 4 kiloparsecs. The second bin is presumably the one you will put on the left, unless there's something I'm missing something.
Yeah, I'm not actually sure which one is the 7th spin. No, but I'm not comparing here to the cooling flow model. I'm comparing here to the isothermal model. Right. So this is the cooling flow model. Isothermal model is just a spike. Right. So here what I'm saying is the comparison to two different models. This is comparison to the cooling flow model. I'm not even showing the plots for that because that's just the cooling flow model does very bad. Isothermal model is what people use instead, but then there the comparison is closer. And I'm not, the 7th here is not the same as the 7th there. I apologize for that. I don't show all the points here. I can tell you what the number is. But
in the grand scheme of things, in your model, the majority of cooling mass is still cooling.
yes.
Some region you get to heat, but most of it just keeps going down.
Right, exactly. But the point is that how much of it is cooling. There is less of it cooling than you would get from cooling flow model because basically you're not fitting this, you're fitting this to the data, and this much is cooling instead of this much is cooling. So if you want to have a model that correctly predicts how much gas is cooling, it should be a model that fits the entire spectrum. And basically the point is that so far people, to calculate how much cooling happens, they fitted this, which doesn't fit the spectrum. So this is a model that fits the spectrum and also tells you how much cooling is happening. And it gives you less cooling than it would get from the full cooling flow, from the pure cooling flow model. Does that make sense?
Well, I guess I'm still trying to understand in the big picture of things.
Yeah.
Gas is cooling.
Yeah.
And
Part of it is cooling, part of it is heating. At high temperature.
in your picture, part of it is heating.
That's right.
And in your picture, the heat that heats it is still coming from the gravitational energy released in the cooling process.
Well, it's not entirely clear where it comes from. It could be from AGN feedback. It could be from other things. The point is that there is a time, whatever it is, it should be set by this time scale. But exactly what the origin of it, it could be anything. Right.
Well, I mean, okay, that case, I still want to understand what so the basic challenge in cooling flows is to come up with a balance between cooling and heating.
That's right.
Now, the basic challenge if you put a AGN in the middle,
Right.
how does it know about the cooling thing coming in?
Right.
People have been stumped to try to couple these two.
Mhm.
These things
Right.
just go out far away. How do they ever? They have no business knowing about CS squared. So
Right.
the normal quantitative statement is that the AGN has got no way of about knowing CS squared, and put the alpha in there. How would it know about alpha? Now, that's why I'm just curious here. So in your picture, you say, well, somehow magically it does know about alpha, and if I
No, it doesn't know. I mean, I think there are two different assessments. One is that you keep injecting energy, but then that energy propagates with the speed of sound, right? And then dissipates with through some turbulent viscosity, right? And the thing that sets the time scale is the sound speed, basically. And then this equipartition assumption.
in an AGN picture, where sure got a lot of energy, and there's a picture that the stuff comes out relativistically.
Right.
It's got nothing to do with CS, going out at sea.
Well, no, but relativistically they come out just in a tiny jet. But then for it to propagate and heat up everywhere, it has to propagate either through weak shocks or through sound speed. Then that's the part that matters. So the relativistic part is a tiny fraction of the gas that's affected by that. Most of the gas would be affected through sound waves or weak shocks. Right? And that's what captured by this picture.
And that's pretty the only picture that's really under consideration here, because it's the cooling itself, but that energy it's a zero-sum game.
Yeah. Right, that's right. That's the only picture. Yeah, there must be a heating source. The interesting thing is that we don't have to know what the heating source is. The only thing we know is that there is a steady state that's achieved because time scales are so short, and then we can model that. Of course, if there is no heating source, then you wouldn't achieve a steady state, right? Good. So we can go further. We can actually now. I fitted all those spectra, and I said most of them give good fits. So you can tell you what alpha you get, and surprisingly, we get the same alpha more or less for everything. We get an alpha which is basically consistent with 0.08 with a small error, and there's a small scatter in it with of order 20%. So basically, the alpha is 0.08, and you have a scatter of order 20% in alpha, or to be exact, 0.017. So that's also interesting that essentially all the clusters already can be fit more or less by a single alpha value for viscous heating. And this is consistent with what you get from direct observations. For example, Hitomi observed the turbulence in the center of Perseus cluster. And it gets around 4% energy in turbulence, but you have to add up the magnetic energy. So that could be as big as 8% or a bit more bigger than that. And people have direct simulations either in the context of accretion disks or for intercluster medium, and you get an alpha, or you get basically a turbulent energy fraction, which is comparable to a few percent, of order 10% or lower, which is again consistent with this number. So this is interesting. So we can fit the spectrum, we can get the Shakura-Sinyaev parameter, which is consistent with other independent observations. And we can get the real thing. This is how much we call them cooling flows, because you make cold gas. And so this looks like having a lot of errors, but I mean, this is the problem if you have a lot of bins in X-rays. But this is the amount of cold fraction that you get if you assume that this cooling flow has been in place since redshift of 1, so around 8 gigayears. And you get a cold fraction. Basically, cold fraction is the ratio of the cold gas you accumulate over the hot gas that you see. And it's about order 1 within 20 kiloparsec or so. It can go up to 10, but it's with large error bars. So you can actually ask how much mass there is. This is a cold fraction, but you could ask what is the total cold gas that you accumulate since redshift 1. And redshift 1 is just a typical redshift. You think that things couldn't be, if they are stable, they should be around for a long time, for example, around 8 gigayears. And here is basically the total cold mass that you get by integrating, either by taking this number or by just taking this cooling flow that you see here and multiply it by 7 gigayears and say how much total cold gas you get. And this is the total cold gas that you predict over 7 gigayears, assuming that it's around over 7 gigayears. And on the horizontal axis is the amount of the stellar mass that you see in this core, in the BCGs, that's it, at the centers of cooling cores. And interestingly, there seems to be basically reasonable agreement. Of course, it could have been much smaller, but it turns out that at least for 4 out of 5, you see that they are more or less in line. That means that a significant fraction of the stars that you see in BCGs, given the errors, of course, could be actually forming from the cooling flow. So the gas that cools, of course, it should form some molecules, but molecules don't stay there very long. They form stars. And if you add the total amount of stars, it turns out if you add the molecules, it doesn't make too much of a difference. It works. So basically, they seem to be in agreement. It could have been much smaller, but it seems that it's not much larger. That means that you don't really overpredict the cold gas. There is this one cluster Hydra A, which you overpredict. And it seems that the interpretation we have for that is that this cooling flow hasn't been in place for too long, maybe about a gigayear or so. So that's why if you assume it's been around for 7 gigayears, you overpredict the amount of cold gas. So that's the first part of the talk. So, and this is a paper that's coming out this evening. So the conclusion is, so we have a cooling plus heating flow model, which improves upon the old cooling flow model. It gives you a realistic and physical X-ray spectrum for cooling flows. It gives a measurement of MHD turbulence in cluster cores. And a reasonable estimate of the cold gas mass that you expect to see. Now, of course, there is much more that can be done. This is a very simple model. You could have more realistic models of multi-phase structure. And really the question is how can you implement this in hydro simulations, given that, of course, in simulations, you don't resolve everything. You have to have subgrid modeling. And one way to actually do this, to implement these cooling plus heating flow models in the subgrid modeling of your hydro simulations. OK, so that's part one. Before I completely switch gear, are there any questions? It's crystal clear, obviously. So let's go to seeing the same thing, or not quite the same thing, but the nanostructure in dark matter. So this is actually a project that has been going on for a longer period of time. Started with work with Ed Bertschinger and Roy Mahayai, but then more recently with my former postdoc at Perimeter and Waterloo, Jesus Zavala, who is now faculty at University of Iceland, and then Mansour Karmi, who is a very good PhD student who's just finishing up with Avery Broderick and I. And there have been other people involved in the project over the time. But so there are theory development and observations, and here are the references. So basically, the gist of the idea here, and again, this is something that I alluded to before, and you've heard before. Dark matter, we believe, is collisionless. This is a cartoon that shows why it is collisionless. It seems that when two clusters come together, the baryons are stuck in the middle. The dark matter, which is seen by lensing in the blue part, and galaxies that you see in yellow, they pass through each other. It seems that dark matter is collisionless with some approximation, of course. And dark matter appears to be cold, at least, again, with some approximation or with some upper limit, given that we seem to be seeing a structure up to wave numbers around 10, or the structures or distance of around 0.1 megaparsec, or 100 kpc. This comes from Lyman Forest. Of course, this is an old figure, but somehow nobody has made a much better one in the past, I guess, 18 years or so. So if dark matter was hot, then you would cut this off. And basically, given the data that we have, mainly from Lyman Forest, you have upper limits on temperature of dark matter. But the basic model of dark matter is cold, is collisionless. So there's basically just one free parameter of dark matter, which is the density of it. Now, if we take that model and try to run with it, one of the things that we kind of discovered over the past few years is that you could understand the structure very well by studying the phase space, in particular what we call particle phase space average density. And what it is it's basically what you go in a simulation or real world if you have the opportunity, sit on a dark matter particle, look some distance delta x and delta v, delta x in position, delta v in momentum or velocity, and ask what is the mean density in the phase space. So that's what it is. But that's why we call it particle phase space average density. So what is the phase space density that an average particle would see at some distance x, or delta x, or let's say delta x and delta v, from where it sits in the phase space. And what this is, what they call sigma here, or I guess usually call it P2 sat, it's a measure of a structure in the phase space. And the reason it's nice are two things. Is that if you believe in Liouville's theorem, which is valid if you have collisionless evolution, then phase space density is conserved. So things basically stop evolving in the phase space, or structures stop evolving in the phase space after things are said and done, or when you basically reach when tidal stripping stops working, then you have stable structures in the phase space. So what that basically means is that you have some structure that you form at some point, and it's stopped being stripped by its environment, then that structure is frozen, and that, as a result of that, this P2 sat is frozen. Every particle basically sees a frozen environment in its neighborhood. So to actually verify that, we went into simulation. This is from the highest resolution simulation of CDM that's available, Aquarius. And you see this blue curve or blue surface shows this P2 sat as a function of distance in position and distance and velocity. So that means that basically if you are a typical particle and you look some distance from where you sit in the position and some velocity difference, basically this would be distance in phase space. This is the phase space density that you see. I think this is units is something like solar mass per kiloparsec cube per kilometer per second cube. And interesting, and the red region is what you get from a smooth halo. So what you get is basically the phase space actually changes by almost 10 orders of magnitude, which is amazing. So you have this quantity, phase space density, that changes by 10 orders of magnitude from the largest scale of the halo down to the smallest scale that you can resolve in the simulation. And moreover, this looks like a very, basically, this goes well above what you get from average halo, which means that it actually captures all the substructure, subhalos, sub-subhalos, et cetera, that I mentioned. Another interesting fact, which I didn't show in a slide for, is that even though this shows 10 orders of magnitude range, the actual CDM, simple models like VIM, predict that this should change by 20 orders of magnitude. So even though in simulation you actually resolve 10 orders of magnitude, there is 10 orders of magnitude more of this that you don't resolve in simulations. So if you want to have a realistic model of substructure, you need a model to capture what happens basically farther down. And the current simulations don't have good enough resolution to tell you that. So the interesting about P2SAT is that it freezes, as I mentioned. And that's something that we verified with some approximation. So these are basically the contours of P2SAT. These are different redshifts. These are different types of halos. These are cluster size halos are black. Dwarf size halos are green. And essentially, if you ignore things that are very far out, because they would be basically boundaries of the halo, things that are farther in, they essentially are on top of each other. So this is something that's more or less universal. No matter when you look, where you look, you always see the same thing. And you can think of this as something like tree rings, right? So you build these things from inside out. The inner regions are places that form early and capture the environment of the universe, how it looked like at early times. The outer contours is like the outer tree rings is basically things that form later. And you form all the halos hierarchically from inside out. So in the phase space, particles that you see close to you, there are things that basically merge your halo at early on. And then there was some dynamical time, but then they froze. And at larger distances, you see things that emerge later. This is another demonstration that this P2SAT is universal. So there's this dotted band that you see. On a smaller scales, depending on the halo that you're looking at, you're limited by the resolution. At larger scales, you're limited by the tidal radius or the size of the halo. But in principle, if you have high enough resolution, and this is something that we have confirmed to some level, basically all of these kind of converge to the same thing at a small scales. And the nice thing about that is that basically this is something you can hopefully theoretically model and then extend it 10 orders of magnitude farther down, where we think the real dark matter particles sit. So historically, this is something that's related to the stable clustering hypothesis that probably a handful of people here know about. I don't know. I know Bailey does, but I don't know others have heard about it. This is something that people who did cosmology before that in the 20th century have heard about. But then it kind of was forgotten. So what we did, we basically revived it, but did it in the phase space and used much higher resolution simulations to confirm and calibrate it. And we have a code that actually models this for a given cosmology, which is publicly available. So you can use that to predict the nonlinear power spectrum down to very, very small scales. So these are the scales that you can get from simulations, and things more or less agree. You can get them from the so-called halo model, or you can get it from our P2SAT model. But then if you go to very, very small scales, the different halo models, there are also some uncertainties in them. You see there is a lot of a scatter in depending on what sort of concentration mass you assume. But the P2SAT has a robust prediction, and we have two different ways of doing it. There is a turns around on this very small scale. This is 10 to the 9, which this is basically a milliparsec scale. This is due to the assumption that I have for the temperature of the WIMP, Basically, this is the freest streaming length of the beam, which makes this turnover. So that's the theory. So we have a theoretical prediction for dark matter nanostructure. And there is this one is called nanostructure literally because it's a milliparsec compared to megaparsec scale, which is a typical size of halos. So these structures on milliparsec scales are things are 9 orders of magnitude smaller than your halos, but you predict them from a standard cold dark matter model. So how can we observe them? That's a new thing that's going to appear tonight. And the main idea is that you have basically you're observing a source, preferably a very far away source, and you have all these substructures and substructures, all the small halos that cross your line of sight. In fact, you can estimate for typical microhalos that are Earth mass, there are around 1 million of these that cross the line of sight to a cosmological source at any time. And these things actually move. And they could cross, because they're small, they're the size of the solar system, they could cross your line of sight within a few years. So if they have any lensing effect on your object, your source, that's going to change over that time scale. Of course, the lensing effect is small. This is something, but then there are a lot of these objects. There are, as I said, 1 million of them. So if you take that into account, you predict fluctuations of order 10 to the minus 3 to 10 to the minus 4 to 10 to the minus 3. In the magnification or in the brightness of the objects. Basically, everything is magnified by some tiny amount, or magnified or demagnified. And that tiny amount fluctuates over there every few years, or on the time scale of a few years. And the amplitude is maybe 10 to the minus 4, or 10 to the minus 4 to 10 to the minus 3, depending on the model. However, if you have a strongly lensed system, like we do, and I'm going to show you some examples, this could be enhanced by more than 100, in fact. So this could become of order a percent level. And this is the formula, basically, which relates the temporal power spectrum of the magnification, which is the brightness of your source, with the power spectrum of dark matter, or all the stuff that are along the line of sight. And you don't have to worry about the details. The point is that the P2SAT predictions would go in here. And this is what you observe when you observe cosmological sources.
Sorry, but
yes.
Is a dark matter only prediction?
This is dark matter only prediction. Now, what happens is the baryons, of course, could change this, but the baryons are expected to be smooth on the scale of the Jeans length, basically, which is large, except inside the galaxies. But these are random lines of sight. Basically they're unlikely to. So basically, most places here, there is no galaxy. There are some places there could be galaxy, and you have to take that into account. But most of these places, basically, you have basically most of the volume is in voids, where there is very little baryonic effects happening. So you have a smooth gas. So that's the key assumption here, and that's kind of the premise of why this is not affected as much by baryonic effects, because most of the universe baryons are hot and they're smooth. The few places where they do form stars, they have very small volume. So they don't affect the typical line of sight. There is one exception to that with microlensing that I'm going to come back to. But that you have to add on top of this. So this is an example of a multiple lens quasar as seen by STSS. So there are multiple 5 different images. And the idea is that you can actually look at the difference between the brightness of these and basically see whether if there is any difference, it could be due to lensing effect. So this is the prediction from P2SAT. This is the variance you expect over time scale. And you see that over 1,000 days, like this would be 3 years, you could get about a percent effect. These are different. I mean, this is a halo model. This is a stable clustering model. So there's some model dependence. So here I show the microlensing effect due to stars, but assuming that there's no caustic crossing. So it's hard to confuse these two with each other. The part that we haven't modeled is what happens if you have caustic crossing. And that's a problem that basically causes that we cannot exactly detect the effect right now. We can only put upper limits. But if we can actually find a robust way of basically distinguishing caustic crossing from this transient weak lensing due to microhalos, then we could in principle detect this effect.
Why do you get 10, it's like 10,000 like 30 years for the microlensing time scale? When I saw people talk about that, tend to talk about time scales of months or years.
But that's the Cauchy crossing.
What's the distinction between these two?
Well, so the question is, yeah, I mean, if you have a singular star, or, well, if, the distinction is that if you have a singular star, you don't have Cauchy crossing. If you have multiple ones and you have a large enough density, then you could, in principle, but can you get infinite magnification? That's a distinction.
Well, isolated star is nothing else, but even a single star in a gravitational shear field has Cauchy.
Yeah, right. So that's the thing. So if you have Cauchy crossing, then that's going to ruin this. And that's why so far we only have upper limits. We don't have exact detection. But then the hope is basically you have some images have Cauchy crossing and some don't. And then the ones that don't have Cauchy crossing, you can get a better upper limits.
I thought the latter one cannot exist because you know that it's a strongly dense system, so you know there's large scale shear.
Yes.
In the presence of shear, all microlenses are caustics. It's a Chang-Mathnow lens like that.
Well, so no, that is fine. So, but if you don't have any macro lenses, then you don't have caustics. Do you agree with that?
Sure,
but that's the statement. So that's why so far we only have upper limits. Because if you agree that if you don't have micro lenses, then that's it, right? So then whatever you add, it should increase the noise, right? So you add micro lensing to the effect of microhalos or to transient weak lensing, and then they wouldn't cancel each other, right? So they would just add to each other. Does that make sense?
I mean, people claim to have detected microlensing.
Well, so that's something we could discuss, right? But then some light curves are noisier than others, and I think this question of whether they have detected microlensing, it's a little bit of dubious, but that's something we can discuss later. So the question is, can you actually distinguish? They think they have detected, assuming that there's nothing else, and then of course if there is this effect, then it's not clear whether you can distinguish the two. But so far we have upper limits. Okay. So let me show you how we did it, and that's in the next. What do you think? How much time I have?
5 minutes.
5 minutes. Okay, in the next 5 minutes. So these are two light curves from SDSS. Or I guess not from SDSS. These are two light curves that from Cosmogray server. So this quasar was detected by SDSS, and it's followed up by this Cosmogray survey for many years. This is part of, I think, half a dozen quasars or multiple image quasars have been followed. So my idea is that these brightness that you see, this is what you observe as magnitude. There's a part of it which is intrinsic to the quasar, which is basically should be the same for all images with some time shift or time delay that's to be determined. There is a lensing part, which would be uncorrelated from one image to another. And there's a measurement noise that you know, basically, if you believe the errors that the observers give you. So then what we do is that we use an MCMC scheme, assuming that these are both Gaussian random fields with some yet to be determined power spectra. But the difference is, of course, intrinsic variability is the same Gaussian random field, which is only time shifted between different images. But then this lensing is uncorrelated from one image to another. And of course, noise is uncorrelated between images and between different times. This is an example. We tested this on mock data. We put in some lensing, and I didn't show you the don't show you the intrinsic one, but it's the same thing. We generate some mock data, and then we can recover the. So this would be the orange point would be mock data, and we can recover the from our pipeline within the errors. This is a so-called time delay challenge. Some of you might have heard about it. So there were multiple groups in the past who tried to measure time delays from these multiple image quasars. And there's this time delay challenge was trying to basically give them some synthetic data in which we know the actual time delay. And then the question is, can your method recover it? And this is how we do. Basically, these are the actual values, and these are the recovered values. Of course, these are very different noise models than we do. But nevertheless, we can get the right time delays. So that's also another confirmation of the model. So these are actual measurements of intrinsic power spectrum for lensing as a function of frequency. And this is so this is intrinsic, and this is lensing power spectrum. These are two independent components. And then there are time delays compared to the reported time delay, which are more or less consistent, not 100% though. And the point is that we can actually go down to errors which is of order the target, which is around 10 to the minus, 1% was our target. A square of that would be 10 to the minus 4. And you could see that actually our upper limits on lensing power is comparable to that. It does get bigger if you go to smaller frequencies, it turns out. And that's where the signal is the biggest. So now this is the data. If you can compare it with simulation, then it said the strongest limits come from the quasar that I showed you. These are these two images. If you actually time shift, use the best time shift that we have, and subtract the mean magnitude, you see that these two light curves are essentially on top of each other. And indeed, the difference is of order of 1%. You see this is, or less than 1%, if you will. This is like 10%, 5%. So we can actually use this and translate this to a limit on dark matter power spectrum using, so the limits are model independent. So these are various quasars. There is some dependence on the size of the disk. And here this is a realistic value for the size of the quasar disk, which is of order 1 light day. And the strongest limit does come from this quasar, which is this black curve. And it's the strongest at lowest frequency. But of course, you could use it at other frequencies as well. And you could translate the frequency to some length scale because things travel with a speed of like 600 kilometers per second. So what you could see that this is LCDM prediction, and this is 5 times LCDM prediction. And when I say 5 times, I mean the linear power is 5 times bigger. So this means that you're basically on the verge of detecting what lambda CDM predicts if you believe this P2 SAD model that I showed you. Basically, this is the deltas. This is what I showed you for prediction. This is the same thing. Although here we didn't put this WIMP cutoff. So if, of course, WIMP is very hot, you're going to cut off everything. So the lesson is that if you take this completely unconstrained region of the parameter space where the power spectrum of dark matter as a function of wavelength is, of course, on larger scales, we measure it as 10 to the minus 9. But at small scales, there are very loose bounds. And then these are really just model dependent. You have this very strict upper limit on the power, which is basically like only a factor of few bigger than the actual prediction for lambda CDM. So it's 3 times 10 to the minus 9, which is up here. And the only thing that's keeping us from making a detection is this microlensing modeling, basically. If you had microlensing, basically, if this effect was there, and then you had microlensing, you should get bigger discrepancy. And assuming that there is no conspiracy between microlensing and this effect, then we put this upper limit on CDM power spectrum, which is very close to the actual value. So that's it. So I think seeing dark matter nanostructure, given what I said about the baryonic physics, that it would be ineffective on these scales, on these places. It will be a clean test of CDM. P2 SAD, I think we've demonstrated this to some level. There's a robust theoretical framework to model CDM nanostructure. And transient weak lensing of quasar light curves I think is on the verge of detecting CDM nanostructure. However, you have these challenges with microlensing and modeling the disk size, which need to be addressed to actually have a detection. OK, thank you. Bailey?
I thought the claims are that the flux anomalies in strong lensing systems are evidence of substructure, nanostructure.
Yeah.
In CDM.
Well, I mean, that wouldn't be what I call nanostructure. That's evidence of, the claim was that it's evidence of substructure. But then, of course, what happens is there's always uncertainty in modeling the lenses, like how aspherical they are. And then if you want to put, higher multiples on the structure of your lenses. So it's been very hard to make that more precise. There have been I guess if you that was like old work by Dalal and Kochanek. Newer work uses SPT sources, which are then resolved by ALMA, and they detect largish subhalos, like I think 10 to the, don't remember, like 10 to the 6, 7 solar mass type things, which of course you wouldn't be able to see at large distances. But here, of course, we're pushing it to much, much smaller scales because we're looking at time dependence. We're not looking for a DC signal. We're looking for a, I guess, AC signal, if you will. We're looking for things that change with time. And if there is a lensing signal which does change with time, it should be on very, very small scale. And of course, it would be much smaller. But given how well these match, you're actually starting to probe very small lensing signals, right? How well these time-dependent things match. But the good news, another thing I forgot to mention, is that things like LSST are going to increase, at least are thought to increase the number of these multiple lens quasars, I think by 2 orders of magnitude, if not more. And then, of course, you're going to have much better data to do this with. Now, whether modeling is going to be as easy, it's not entirely clear. I think the main challenge, as I mentioned, there are 2 main challenges. One is trying to distinguish microlensing. And in fact, in our original paper, our idea was that the microlensing is expected to be a non-Gaussian signal because basically you only have a few stars that contribute at any time. But this translated weak lensing is expected to be a Gaussian signal. So if you have a very high signal-to-noise detection, then in principle you could look at the Gaussianity of the signal and see whether, whether it matches what you is it very Gaussian or very non-Gaussian. Or in principle, you could separate it into the 2 components. There might be better ways of doing this, but nobody has worked on that. And the other part is the size of the disk, which is really what happens is that if you look here, the limits become very bad here because the size of the disk is big. So basically, on smaller scales, if your dark matter subhalo or microhalo becomes smaller than the disk of the quasar, it doesn't do anything. And there's some uncertainty here. So if you could actually make this, depending if you know this size better, then in principle you could go farther down in principle basically. But right now the strongest constraint comes from the bigger scale. But you're right. Right now the claim is based on the time-independent signal, and we want to push it in the direction of time-dependent signal. Other questions? Okay. Well, thank you very much.